This is Math 30-2 with Mr. Wagner, and today we're looking at logarithmic functions. Now, you should have completed a math lab where you explored logarithmic functions a little bit, and having done that, that'll set you up for getting into more of the details in this lesson. So as we look at this lesson, you'll see here two measures of success. So first, we want to think about what are inverse operations and inverse functions. That's where we'll start today. And then we'll talk about similarities and differences between this exponential function and this logarithmic function. So we have 4 warm-up questions here. Pause the video at this point, complete these 4 questions, and then restart the video, please. Pause now. Well, hopefully that was quick for you. How do we undo adding? Well, we subtract. How do we undo dividing? We multiply. How do we undo squaring? We square root. And how do we undo taking the sign of an angle? Well, we would do what's called the inverse sign, which is the sign to the -1 on your calculator. And just to kind of focus in on this one a little bit, this is going to help us understand as we move forward here. So if we think, if I take the sign of something, oh, what can it be? Well, when we take the sign of something, it's the sign of an angle. So sine will operate on angles. And if I do the sine of an angle, well, if you remember SOHCAHTOA, so sine is opposite over hypotenuse. So what it gives me is it gives me a ratio of 2 sides. And in this case, it's the ratio of the length of the opposite side compared to the hypotenuse. Inverse sine works backwards. It takes that ratio of opposite over hypotenuse, and it takes that as input. And when I do the inverse sine of that ratio, what it gives me as output is the angle measurement. So that's something you've done since grade 10. But it's going to help us as we move forward here, because that's an example of what inverse operations do. Operations like adding, subtracting, multiplying, and dividing that undo other operations, they're called inverse operations. Functions that undo what another function does to a variable, those are called inverse functions. So it's a similar idea, but now we're working with functions, we're not just working with operations like this. Although here we could say the sine of an angle, that's a function. Inverse sine of an angle, that's also a function. So let's think about functions for a little bit in a more visual way. So here, I like to use this shape here to represent a function. And so what's going to happen is I'm going to put in some input at the top here. A little messy, but that says input. And then out at the bottom, I'm going to get output. Now, acceptable input, these things are called elements in the domain for my function. And here, the stuff I get as output, well, all the set of possible outputs that describe elements in the range of a function. Often with function notation, we would say this could be something like O f of x. So that's how we think of functions in math. But what we could do is we could just imagine things a little bit differently here. And suppose what I have is a machine that is a juicer. So there's certain input that I can stick in my juicer, and it'll give me some output. Now, just to make sure I can catch my output, I'm going to put a pot down here. So let's just imagine. If I was to take this apple and stick it into my juicer, is that acceptable input? Yeah. We would normally say that's acceptable input. What it's going to give me out will be apple juice. Could I take this orange, put it into my juicer? Yep. What do I get out? Orange juice. So those two, apples and oranges, are elements in my domain. They're acceptable input for this function machine. Now you see here some bricks. Can I put bricks into a juicer? No, I cannot. These bricks are not part of the domain. So these are not in the domain for my function, my juicer function. Now suppose there were some magical way that instead of just having a pot here, I was to take another machine here, and if I was to create some kind of unjuicer, so that if I was to start up here and I was to take this orange and stick it in through here, what I'd get output, orange juice. So suppose I could stick in an orange, and there I'm going to get some orange juice out. Now let me see if I can pick something that's a little bit orangish in color. There we go. So I get some orange juice. And if that's going to be my output, suppose that was to become input into my unjuicer. Well, just use your imagination and pretend that my unjuicer could basically undo what my juicer did and give me an orange back out at the end. These two functions we would say are inverse functions. One function undoes what the other function did. So if we thought a little bit more mathematically, what we would say, because we often use variables to represent things, suppose I was to take and stick an x into my function. My function machine, well, let's say it's not a juicer anymore, now it's some f of x. It's going to take this x as input, and what it's going to put out is, I don't know, some value f of x. If that f of x then goes into here, becomes input into my next function, let's move that orange juice, that's going to be my output and input. What am I going to get out at the end from this inverse function? Well, it'll be an x again. So if I had an x at the beginning here as my input, my f of x does something to it, then my function here, we would say that this would be, let's get a marker that works. Inverse functions have exponents of -1. So we'd say, oh, f to the -1, this function undoes what that function did. Okay, this notation we don't have to use for this course, but notice how it's the same notation as we had here with the sine function. And we didn't say that this is 1 over sine x. No, this was the inverse of sine x. It took the output from sine x as its input, and then it gave me output, which is what was initially put into the sine function. So again, let's look at that here. Suppose this is going to do the sine of something, then this function would be doing the inverse sine of that something. And again, I would have an angle that I'd stick in here. My sine would give me out a ratio. I'd put the ratio into here. The inverse sine would give me the angle out again at the end. So that's how functions and their inverses work. So let's look at that with some examples here. We want to write a function g of x that will undo what f of x is doing to the variable. Well, f of x is taking the variable and it's adding 5. So g of x could take the output from that and subtract 5. So this would be the inverse function of what we initially had in the f of x function. So let's think of this with function machines. Suppose I was to pick a number for x to stick in, and this is a good way to test to make sure I've found the inverse function. Let's go with red here. Suppose I pick a 3 as my input. So I put in a 3, so this x becomes a 3, plus 5 gives me an 8 as output. Well, that 8 replaces this x. 8 minus 3 gives me 3, and so my output for the inverse function is the same as my input from the original function. So that's a good check that yes, I found the function that will undo what f of x was doing. I found the inverse. Well, let's look at number 6. Question number 6, how do I undo dividing? Well, let's do the g of x function. How do I undo dividing? I multiply. And I still use an x here. These two x values will be different because they take different inputs. So then let's do the check to see if I drag this out. And let me pick a number for x. Suppose I say x is equal to 42. If I stick 42 in here for x, then I get 42 divided by 7, which gives me 6 as output. If I take 6 and I multiply it to 7, that gives me 42. And the input in the original function is the output after it's passed through the function and its inverse. Well, let's look at number 7. Square rooting. Well, how do I undo square rooting? I square. So my g of x function could equal x squared. Then again, let's look at this function machine. Suppose I pick something to stick into my square root. Let's say I put in 16. When I square root 16, that gives me 4 as output. Notice this is a positive, even though there's no sign in front. That means we want the principal root, the positive square root. So then if I put a 4 in here and I square the 4, what do I get? I get 16. Input into the original function equals output after it's traveled all the way through the function and then its inverse. Next one, tangent. Well, similar to sine, how do we undo tangent? We do the inverse tangent. So what will this look like for our function machine? Do I have space for it? Let's stick it there. And let's pick a number like 45 degrees. If we put 45 degrees into the tangent function, we are going to get 1 as output. If I do the inverse tangent of 1, I get 45 degrees. Well, what's the point of all of this? Well, yeah, it is to understand functions and their inverses, but even more, it's to understand what's the inverse of this exponential function. How do I undo putting a variable in the exponent or putting a number in the exponent? Well, the answer is we take the logarithm. So this would be the log base 10 of x. So here's what would happen. Move this over here. Suppose I was to put a number into my exponent here. Let's say I stick in a 3. This 3 becomes the exponent, so I have 10 cubed is 1,000. If I was to stick 1,000 into my log base 10 function, just like all these others, it's going to undo what the exponential function did, and it's going to give me 3 as output. So here's what's happening. The logarithm base 10 looks at this x, and it says, this x value, which is 1,000, if I was to rewrite this 1,000 as a power where the base was 10, what would this exponent be? Oh, well, we already know 10 cubed is 1,000. Oh, so that exponent would be a 3. That is what the logarithm function is telling me. What the value of this exponent would be if I was to rewrite this 1,000 as a power base 10. So let's summarize some information here. Exponential functions, as we learned in chapter 6, may give us a curve that kind of goes up like this, and we'd say that would be exponential growth. Or we could have a curve that starts up here and then it comes down and approaches the horizontal asymptote, and we'd say that would be exponential decay. So we could have either one of those curves. As we looked at domains, ranges, asymptote, all of that information for the exponential function, domain is all real numbers. Anything from negative infinity to positive infinity, we can always get a graph. What's the range? Well, the y values are greater than 0, not equal to, because we never touch this horizontal asymptote, which we have here. Horizontal asymptote is y equals 0. That's the x-axis. What are the x-intercepts? There are no x-intercepts because we never touch the x-axis. What is the y-intercept? Well, notice I have no number multiplied in front of this b, so the y-intercept is at 1. Let's look at this logarithmic function. Well, for the exponential graph, if the base b was bigger than 1, we had growth like this. And here for the logarithmic function, if our base b is bigger than 1, we get a graph that curves and goes kind of like this. And if we have a base that's between 0 and 1, then our graph comes down and goes like this. Not a pretty curve, but your calculator will do better than me drawing on a tablet. So here's what we find. They are inverses of each other, which means now where here x could be any real number, here y could be any real number. So we'll notice that the domain and range have flipped. For the logarithmic function, y can be any real number, but x has to be greater than 0, not equal to 0. So we have this vertical asymptote now along the y-axis. So vertical asymptote is y, or x equals 0. So notice here how this y changed to an x up there, and this x here changes to a y down here. This y changes to an x. That's a characteristic of inverses. We don't spend much time getting into it in this course, but you get inverses by interchanging x's and y's. On the exponential function, we had no x-intercept. Now we have an x-intercept of 1. So again, this y becomes an x equals 1, that's the intercept. This x becomes a y, and there's no y-intercept for the logarithmic function. Now, log base b of x equals y. This means exactly the same thing as b to the y equals x. So remember, a logarithm takes a number as input, takes a power as input, and gives me an exponent as output. So here you can see that exponent for the y. Next bullet. These words, really useful to get in your head. So here's what a logarithm is saying. If x is written as a power with a base of b, so a logarithm says, if I take this x and I rewrite it as a power where the base is b, so I'm saying x is equal to some power where the base is b, its exponent will be y. And so it's saying this logarithm, if I take x, rewrite it as a power base b, the exponent is y. So x is equal to a power with a base of b, the exponent is y. So from this, we discover that a logarithm is an exponent. I will ask you this question many times. The question is, what's a logarithm? And your answer will be, oh, Mr. Wagner, a logarithm is an exponent. Now, is it exactly an exponent? Well, sort of yes and sort of no. Let's look back at this question for a moment. Here, if I look at this exponential function and the logarithmic function there, maybe I'll clean up some of the things here. Get rid of that and get rid of this. There we go. Here, the logarithm as input, it's taking this 1,000. Where did this 1,000 come from? Well, that was a 10 cubed. So this logarithm takes this power as input, even if it's not written as a power, and it says, if I was to rewrite this 1,000 as a power where the base is 10, so here this is the 1,000, the logarithm gives me the exponent as output. Well, there's my exponent, 10 cubed, so the logarithm gives me this exponent as output. That's why I say a logarithm is an exponent, because that's what it gives me as output. So back here, a logarithm is an exponent. What did it operate on? It operates on a power. The power may not look like a base and an exponent, but we think of it as though it were a base and an exponent. Okay, a little more information. If I have y equals b to the x, that's an exponential function, and it has no x-intercept, but it does have a y-intercept of 1. And again, we looked at that up here, where we said this exponential function doesn't have an x-intercept because of that horizontal asymptote. It did have a y-intercept of 1. Similarly, if I look at the logarithmic function, it has no y-intercept, but it does have an x-intercept of 1. And again, that's in the table that we looked at above. So this logarithm here, notice, is a little bit different from the logarithm we had written up here, where up at the top here we had this little subscript of b. So notice this isn't a base and an exponent, so the x is not an exponent. The b is a base though, so don't think of this as being a power, pieces that go together. The log base b is like what's operating on the x. So imagine the x is separate there. So here we have the log base b that's operating on this x. But here there's no base. When there's no base, we say it's a base of 10. And we call that a common logarithm. So just like this log base b of x equals y means b to the y equals x, this log of x equals y means 10 to the y equals x. So again, if there's no base given, then we assume that it's a base 10. So often when there's a base 10, we don't write it in, but we could put in the base of 10 here. Then as you look at the next one, this doesn't even look like a logarithm, but it is a logarithm. This is the same as the log base e, where e is Euler's constant of x equals y. So this is the same thing as this. So again, that means the base is e, a logarithm is an exponent, so the exponent is y, because it equals the exponent. And all of this is equal to the power that the logarithm is operating on, which is the x. We call this a natural logarithm. So what e is to logarithm and exponential functions, it's kind of like pi to circles and geometry. It's just a constant that has all sorts of useful applications. Now, depending on the value of b, the graph of y equal b to the x And log base b of x may look like one of these. So here, this is the logarithmic function. So this would be y equals log base b of x. For both of these, here, if we have a b value that is greater than 1, if the b value is between 0 and 1, then our graph decreases like this. So that's what those logarithmic graphs look like. And again, we did look at sketches of them at the top of the page. Those weren't so pretty. These look a little better. Y equal b to the x and y equal log base b are inverses. Inverses are reflections in the diagonal line y equals x. So y equals x is a diagonal line that goes across here. And so we'd say that is the inverse of the exponential function that curves down and kind of looks like this. Okay, so this would be y equals b to the x, would be this graph. And here, sort of swooping up like that, that would be the exponential function graph. And you can see it's a reflection, if I'd drawn it better, in this diagonal line. The domain of y equal b to the x is the range of y equals log base b of x. So here the exponential function, the domain is all real numbers for the blue graph. Here for the red graph, the range is all real numbers. Similarly, the range of the exponential function is the domain of the logarithmic function. So here the range of this blue graph, y is greater than 0, that becomes the domain of this red graph, x is greater than 0. So there's a lot of information about logarithmic functions and how they're related to exponential functions. So some practice questions here to work on as well. And that ends our introduction to logarithmic functions.